talk on elastic and material instabilities in hyperelastic materials. This is joint work with my MSc student, Mr. Kunal Patil, who is continuing on for a PhD now. So let us motivate this particular problem first. So unlike in the Newtonian case, or in the case of Newtonian fluids, the second law of thermodynamics puts no restrictions on the form of the strain energy density function for a hyperelastic material. So just to give an example, in the case of a Newtonian fluid, the second law of thermodynamics will put certain restrictions on the viscosity coefficient. So that can be proved. But in the case of hyperelastic material, so I'm talking of nonlinear hyperelastic materials here. So in the case of a hyperelastic material, the second law poses absolutely no restriction. So basically you just get that the stress is the derivative of the strain energy density function, and that's it. So but it doesn't put any restriction on the strain energy density function at all. So mostly the search for reasonable restrictions has been based on physical arguments. Okay? And so that search has continued to this day. So lots of papers keep appearing on what reasonable restriction should be on the strain energy density function. And actually, so this is a very classical problem in nonlinear elasticity. So maybe all the way from maybe 1950s, people have been trying to find reasonable inequalities and so on, right up to this day. So several constitutive inequalities such as the Baker-Erickson inequalities, the Coleman-Knoll inequality, the strong ellipticity condition, and so on and so forth, they have been proposed in the literature. And these inequalities are not equivalent to each other. So it is clear that at least some of them are wrong because mathematically they are not equivalent, and so some of them at least are inadequate to model the actual physical behavior. Okay, so what is this actual physical behavior that we are trying to model? So so basically that is encapsulated in this statement here, that basically we want that the stress should increase with strain. Now this is a verbal statement, okay, and you want to convert that to some kind of a mathematical representation. And that is the reason that it is such a difficult problem, because if we were living in a 1D world, then it would be very simple. Suppose if tau is my stress and if epsilon is my strain, I simply say that delta tau times delta epsilon is greater than 0, right? Because if delta epsilon is the increase in strain and delta tau is the corresponding increase in stress, then just their product is greater than 0. That will sort of settle the question once and for all. But the complications arise because it's a 3D problem, right? And so converting this notion that stress increases with strain, to put it in a mathematical form is where all the struggle is, and that is the reason that you have so many inequalities and so on and so on. So we will propose our own inequality here, which we term as the true stress, true strain inequality, which will abbreviate as TSTS. And this basically seeks to quantify this notion that stress increases with strain. And our work will be restricted to isotropic materials. And the violation of this inequality means that the behavior is non-physical. Okay? Let me hasten to add that I am not considering plasticity, strain softening, and so on. This is, basically I am living in a very idealistic world here, where all the materials are hyperelastic. So I am not considering strain softening and things like that for this particular this one. Okay. As I said, that basically for an ideal hyperelastic material, we will try to quantify this particular statement. And we will also propose a criterion for identifying elastic instabilities, which is a different problem, but we'll try to do that. So this is just some background material. I will run through this quickly. If most of you are not interested in the maths, that's fine. But without these details, it is impossible to state the problem. So if lambda I are the distinct eigenvalues of a symmetric tensor, then the spectral decomposition is given in this terms, where these lambda i's are the eigenvalues of the symmetric tensor, and p's are what are known as the projections. And these are some of the properties that the projections obey. So they are orthogonal, you can say in some sense, that P1 will be P1, P2 will be 0, and so on. So that is what is encapsulated here. And they can be given explicitly in terms of the symmetric tensor by this particular formula. And this actually this works in any dimension. Mostly I will be restricting my work to 3D to the 3D case, but this works for any dimension. And this K here is the number of distinct eigenvalues. Okay, and mostly the criterion that I will be describing will be in terms of fourth order tensors. So we need these tensor products here. So these are the two tensor products that I will need, and these are fourth order tensors. These are defined in this particular way. So here this I will just call as A dyadic B, and here A square tensor product B, because it is a square. So there are no names for these things, but I will just make up my own names here. So the initial notation versions of these tensor products are given here. And these are some of the properties. Anyway, I think probably, I mean, these mathematical details I will probably skip, but you can prove some of these things here. Fine. Okay, then you need some more fourth order tensors here. So these are the identity, transposer, symmetrizer tensors. So what they do is the identity tensor, for example, if it operates on a symmetry, if it operates on a second order tensor, it gives the second order tensor itself. So that's why it is called as an identity, fourth order tensor. The transposer, if it acts on a second order tensor, it gives its transpose. So that's why it is called as a transposer, that this object here. And then there is a symmetrizer, so it symmetrizes the tensor. So that means it gives half of this one. And then there is a relation between the symmetrizer, the transposer, and the identity, which is given by this particular relation. And again, these are some standard notions from fourth order tensors that I will need. So this is like the inner product between two second order tensors. So that is just Aij, Bij. And then the transpose of a fourth order tensor is denoted by C transpose. And that is defined exactly like the transpose of a second order tensor. So for a second order tensor, you would have a vector here and a vector here. Okay, and then you would have the transpose of a second order tensor sitting here. Now because this is a fourth order tensor, it's a generalization of that concept. So here this is now a second order tensor, this is also a second order tensor, and this is how you define the transpose of a fourth order tensor. And it is said to have so now because it's a fourth, for a second order tensor, it is enough to talk just of the symmetry, that Tij is Tji, then we call it a symmetric. But here you can have minor symmetries and major symmetries, because now there are 4 indices associated with a fourth order tensor. Now there are these 4 indices associated with that, and so it is said to have minor symmetries. So this is sort of an abstract way of writing it, but I think many of you will be familiar with this one. So that means if you interchange the j and the I, then if it remains the same, or if you interchange the k and the l, and if it remains the same, then it is said to have minor symmetries. So that means in these first 2 indices or the last 2 indices. So that then it is said to have minor symmetry, and it is said to have major symmetry if you interchange now this whole ij with k. Okay, so if ij kl is kl ij, then it is said to have major symmetry. And the positive definiteness is also defined in a similar way as for second order tensors. So here you would have a vector. In the case of a second order tensor, you would have a vector here and a vector here. Now because this is a fourth order tensor, you have a second order tensor here, a second order tensor here, and this is a fourth order tensor here. So I mean basically these are generalizations of notions in for second order tensors, and just you are using, you are generalizing them not to the fourth order case here. We'll need all this, that's the reason I am defining all of this. So if C has both the minor symmetries, then you can write the eigenvalue problem in this particular way. This C, S here is the eigentensor, just like you have an eigenvector. Now this is the fourth order tensor, and this is now an eigentensor, and this is the eigenvalue, and so it's very similar. So now, because it has minor symmetries, we can represent it as a 6x6 matrix. And then in that case, you will have 6 eigenvalues now for this fourth order tensor. And as I already pointed out, that this S are the corresponding eigentensors here. Okay, and you can show, so similar to the symmetric second order tensor case, you can show that C is positive definite if and only if all these 6 eigenvalues are positive, are strictly positive. So just exactly like in the second order tensor case, if all the 3 eigenvalues, if you are living in 3-dimensional space, if all the 3 eigenvalues are strictly positive, then the tensor is positive definite. So now here, if all the 6 are strictly positive, then yeah. Again, this is just some maths which probably I can skip maybe. This is just, these are now manipulations. So you will need to differentiate these 4th order tensors and so on. So if there is a, so here you can see that if there is a multiple, scalar multiple of a second order tensor and you are differentiating that with respect to a second order tensor, you will get a 4th order tensor. So these are again using those dyadic products that I told you about. So now basically it's a derivative of a second order tensor with respect to a second order tensor. So that will give a 4th order tensor. And so these are various things. So this is like this is a product of a scalar with a second order tensor. This is a product of a second order tensor with a second order tensor, which is another second order tensor. And so it gets into some technicalities which I think probably not very important. But these will sort of be needed if you want to do all the detailed manipulations that come later on. And so these are some, using these results, you can derive some further results regarding the derivatives of second order tensors with respect to the second order tensors. Okay, then we'll also need what is known as a logarithm of a second order tensor. Actually, it can be defined in a very general way. But fortunately for us, we will need only the logarithm of a symmetric second order tensor, and for that you have this very simple expression for the log of a second order tensor. That just turns out to be the summation of the logarithm of the eigenvalues of that second order tensor times the projection. Okay, so that can be proved very easily actually. And then you can even differentiate this. So you can find the derivative of this with respect to B itself, and then some complicated expression in terms of the projections here. So this log of B is something important in this work. So that is the reason I am putting this up. Later on, we will define a logarithmic string, and so that for that we need these expressions in order to define the logarithmic string. So. Okay, so now just so that was just the mathematical background. Now a little bit of background on elasticity itself. So this is the typical convention that is followed in nonlinear elasticity. Capital X is used to define the position vector in the reference configuration. Small x is used to define or denote the position vector in the deformed configuration. And the domains are denoted by V0 and V. And we have some mapping x equal to chi of capital X. I will consider only the static case, and the deformation gradient is just the gradient of this chi map here. This is known as the left Cauchy-Green strain tensor, that is FF transpose, and this one here is known as the right Cauchy-Green strain tensor, that is F transpose there. And then you can use the polar decomposition. You can decompose it as RU or ER. Where this U is the square root of C and this V is the square root of V. Okay, and then so let P and S now denote the first and the second pure order process. So the problem with nonlinear elasticity is that the deformed configuration is not known a priori. So if you are applying some pressure load on a cantilever is deformed, right? And then you do not know where the new boundary is on which to apply the traction boundary condition. So typically, while solving problems in nonlinear elasticity, you map everything back to the undeformed configuration or the reference configuration, and then you solve the problem on the reference configuration. And these measures of stress, this P and S, the first and the second pure order of stress, are defined on the reference configuration. S actually P is like a mixed tensor, but we are again not getting into that. But S is a tensor that lives totally on the reference configuration, and this is like a mathematical device. S is not actually a physical stress. It is a mathematical device that is used to solve nonlinear problems in elasticity by mapping everything back to the reference configuration. Okay? But what one has to remember is that tau is the actual stress tensor. So that is known as the Cauchy stress tensor. So that is actually the stress that is experienced by the material. But the only reason that we don't work directly with tau is because, as I said, you do not know what the deformed configuration is. And so you map everything back to the reference configuration, solve the problem in terms of S, which is the second Euler-Markov stress, and then come back to the deformed configuration and then find out tau. So, okay, how does one define an elastic material? So an elastic material is one where the stress at a point depends only on the deformation gradient at that particular point. You can actually, in principle, the stress at a point can depend on points in the neighborhood, on the deformation gradient of points in the neighborhood, or it can depend on the history of the deformation gradient. So all those things we are saying it doesn't depend. And such an idealistic material we call as an elastic material. So it depends only on the deformation gradient at that point and at that instant in time. Of course, here I am considering only statics problem, but also the deformation. So we are not considering any history dependence and so on. The stress is dependent only on the deformation gradient at that particular point. So that's how we define an elastic material. Then a hyperelastic material is a subset now of that, the special case of that, where you say now that it is an elastic material for which there exists a strain energy density function such that this first Euler-Markov stress can be expressed as a derivative of the strain energy density function with respect to the deformation gradient. And you can use all these axioms of frame indifference and so on to show that the strain energy density function depends on the right Cauchy-Green strain density. Okay, so then the second Euler-Markov stress can be expressed as a derivative. All this is standard material which is known for a very long time. So, but this is just the background for this problem. And if the material is isotropic, then there exists a function which depends purely on the invariance. So the dependence on C goes to an dependence on the invariance of C, which are also the invariance of B. So you can express it in this particular way. So basically, to summarize, if the material is isotropic and if you assume frame indifference, then the strain energy density function is a function of the principal invariance of either the left Cauchy-Green strain tensor or the right Cauchy-Green strain tensor. So that is what is summarized here. Okay, then once you know that, then you can again find out what the stresses are and so on. So again, these are just derivatives of the strain energy density function with respect to C. Okay, and so that we can find. You can also express actually the Cauchy stress, which is the actual stress, as a derivative with respect to the logarithm. Okay, so this log of B, this I will give it the symbol n, just arbitrarily. So one can show that this j tau by 2 is some derivative of the strain energy density function with respect to n. And n is this log. So okay, so this is now the main thing actually in this talk, that tau is the true stress and n is a measure of true strain. This is a logarithmic strain. So in the reference configuration, you will see that B will be identity for the reference configuration and you will get n to be 0. So there is no strain in the reference. We are assuming that body is undeformed in the reference configuration, and so this is a true measure of strain and this is a true measure of stress. And so the criterion that we will propose later will be in terms of this tau and n. So this is so that is the reason that is important here. Okay, now let us look at some background material for what are the criteria, various criteria that others have proposed. In order to understand that, we need these tensors now. So this is the first elasticity tensor, which is the derivative of the first Euler-Markov stress with respect to the deformation gradient. And since in general these both are unsymmetric, A does not possess minor symmetries. But if it is hyperelastic, then it will possess major symmetries but not minor symmetries. So that's what's written here, that it possesses major symmetry but not minor symmetry. Then the second elasticity tensor is defined as the derivative of the second Euler-Markov stress with respect to the right Cauchy-Green strain tensor. And here, since both S and C are symmetric, C has both minor symmetries. And if you assume the material to be hyperelastic, then it has major symmetries as well. Okay, so it does. So this these are the tensors which we'll use to formulate these inequalities. Okay, so this is the tensor that we will propose our condition in terms of this. So this is sort of important for this talk. So this we define as the derivative of the actual stress, the true stress, which is the Cauchy stress, and this is the true strain. So this is the derivative of the true stress with respect to the true strain, and that will just give. So this is the tensor we are defining ourselves. So this is not there in the literature. So this is just our own definition, and it has both minor symmetries because tau is symmetric and n is also symmetric. So it has both minor symmetry, but not necessarily major symmetry. And this objective and all we can skip. And this is just an alternative expression for this z. There is another tensor that is closely related to z, which was proposed by Hill. And so instead of tau, he uses j tau. This j tau is what is known as the Kirchhoff stress tensor, and that is the derivative basically of this Kirchhoff stress tensor with respect to n. So there is one Hill's criterion also, so we will be discussing that also. Okay, so now we will take a look at what are the existing restrictions that are there in the literature, and then we will see what are the shortcomings that are present in these existing inequalities. And so we assume that the reference configuration is a natural state. So natural state means just that it is stress-free, and that your A is the first elasticity tensor, that is positive definite, and so that is equivalent to the conditions that 3 lambda plus 2 mu is greater than 0 and mu is greater than 0. So these restrictions are similar to the ones in linear elasticity, if you are familiar with that. Lambda and mu are the Lame constant. So now, I cannot run through all the inequalities because there are many of them, but just I will give some typical examples of existing inequalities. So these are some of the well-known inequalities in the literature. One is this Baker-Erickson inequality. So if tau I denote the principal Cauchy stresses and lambda I are the stretches, then tau I minus tau j times lambda I minus lambda j is greater than 0 if the principal stretches are not the same. Okay? And this is for I equal to 1, 2, and 3. So we will see that this is ineffective in detecting a material instability. So, okay, what do we mean by material instability now? So the way we are defining a material instability is if the strain increases but the stress decreases. And we are talking of the true stress now, not of the artificial measures of stress like the second tier of Kirchhoff stress and so on. We are talking of the true stress. So if the strain increases but the stress decreases, we are calling that as a material instability.
What do you mean by strain increases?
Roughly speaking, if I just take a rod and just stretch it, roughly speaking, that is what but more rigorous things I will give much later. But roughly speaking, just change in length per unit length. That roughly speaking, I'm saying that right now. Let's just stick to that. So yeah, because it is a tensor, it is difficult to define what we mean by strain increases. You're right, but yeah. But that's why I said that to bring the verbal down to the mathematical is the difficult part of all of this. So in this particular case, I'll actually show the graphs and all that, so that will be able to work. And then the tension extension inequality is that the increment in the stress times the increment in the stretch is greater than 0 for I equal to 1 to 3. So here is a uniaxial tension case where the lateral surfaces are traction free and the end surfaces have some prescribed traction. So we have tau 1 equal to tau 2 equal to 0. Now because the lateral surfaces are traction free, you have tau 1 equal to tau 2 equal to 0 and tau 3 equal to t bar. And then by varying t bar, you can get the lambda 1, which is the stretch in the transverse direction, to either increase or decrease while tau 1 just stays constant. So that's why this inequality is correct, because incorrect, because basically it just comes out to be 0. You do not get the strict inequality here. So, similar shortcomings are there in other inequalities also. So let's look at the Coleman-Knoll inequality. So this was of course proposed by Coleman and Knoll, and it says that the first elasticity tensor should be positive definite. But this shortcoming actually has been known in the literature. This I am not pointing out. This other researchers have also pointed this out, that basically it precludes non-uniqueness of solutions like buckling and so on, Because if you have this positive definiteness, then basically you will not get this complete. You cannot get non-uniqueness of solutions basically. So hence this is not a realistic constitutive assumption. And if you have H in the form of A adding B, then this condition is said to be the strong ellipticity condition. So basically you just replace this H by A adding B here. And then that is greater than 0 for all A and B non-zero. And then the necessary and sufficient conditions one can show for this are that mu should be greater than 0 and lambda plus 2 mu should be greater than 0. Okay, but if I impose that lambda plus 2 mu is greater than 0, then the bulk modulus need not be positive. So in some sense, you want the bulk modulus to be positive because if you are compressing a sphere, for example, then the stresses should all come out compressive. Okay, so that is encapsulated in this lambda plus 2 mu by 3 should be greater than 0. And so this inequality does not imply this. Okay, and so this is a very important physical requirement. And so it is so basically the strong ellipticity condition is not strong enough to ensure physically reasonable behavior. Okay, so that is one shortcoming of the strong ellipticity condition. Then polyconvexity is a condition that has been proposed by Paul. It's a very famous and very well-known condition. It has been used to prove existence of solutions in nonlinear elasticity. That's a very classical work, I think in 1977 or something like that, in Archives for Rational Mechanics. So for the first time, John Ball proved existence of solutions for nonlinear elasticity using this condition. However, this condition is a purely mathematical condition. That means there is no direct link with any physical condition there. And here what we find is that if you take this large scope material, people have shown in the literature that it is polyconvex. However, it displays this material instability, again in the same sense that the stress increases with increase in strain. And even for a Savena, which is known to be polyconvex, there is no criterion based on polyconvexity that predicts the exact strain state at which the material instability arises. Okay, so I think, so those are all the existing things. There are some more, but I will not discuss those in view of the time restrictions. So now I'll come to the proposed criterion here. Basically, as I said, that the whole idea is to try and quantify the notion that stress increases with strain. Right? So how do I do that? So let B, okay, here this T, it can either be actual time or it can be pseudo time, as in load steps. So it can be a statics problem with load steps. So this T1 need not be actual physical time, it can be some pseudo time or something like that. But basically P1 and P2 are two strain states, let's say. And the N1 and N2 are the corresponding logarithms of those there. So this is a left Cauchy-Green strain tensor, and then there's a logarithm of that. And so tau 1 is the stress corresponding to this N1, and this tau 2 is the stress corresponding to this N2. Okay, and so the necessary and sufficient condition now that we propose for this material stability is this particular thing. So basically the increment in stress, they have an inner product of the increment in stress with the increment in the true strain should be greater than 0. So this is the true stress and this is the true strain. We are proposing that the inner product between them should be greater than 0. Equivalently, you can show that this condition, if and only if, that Z, which is actually the derivative of the stress tensor with respect to the N. Okay, so that so one can show that this is equivalent. So that this implies this and this implies this. And because Z is not symmetric, it need not necessarily have major symmetry. So basically you have to look at the symmetric part of that, because the anti-symmetric part does not contribute to the positive definiteness. So you can take only the symmetric part of this. So that is just Z plus Z transpose divided by 2. So this is the criterion that we propose, and basically we will show by means of several examples now whether it succeeds or not. So that's basically will tell us whether this is a reasonable criterion or it's not a reasonable criterion. So I'll show several examples now where I actually apply this criterion now. Okay, so what about Hill stability criterion? So Hill stability criterion is actually in terms of the derivative of J term. But the problem with this criterion is that the Kirchhoff stress tensor is not a measure of the true stress. So it's a that factor J is there, and that makes a difference actually. So that I will show in the later this one. And so many times it does not yield correct predictions. So his criterion is that this tensor should be positive, right? Whereas ours is that Z should be, where Z is the without this J factor. This Z is the same as this one, except that this J is not. Okay, so now basically how do we actually check it? So just like in the case of we check the positive definiteness of a second order tensor by checking its eigenvalues. In the same way, we check for the positive definiteness of this SZS by checking the eigenvalues. So we basically actually, so it has to be tested for all possible deformations, but that is not possible. So what we do is we test it under, let's say, simple cases, homogeneous deformations, uniaxial, biaxial, or triaxial loading conditions, and then try to check the positive definiteness in those cases. So that we sort of consider as the most critical case, let us say, and then try to find that. So basically, you just increase the load, let us say, and see if things break down beyond a certain load. That will say whether the material has a material instability or not. Within the context of, you can embed this criterion within the context of a finite element code by checking it at every cross point or something like that. So you can, you can have a numerical implementation of this within a finite element code also. Either you can do it theoretically or numerically also. And as I already mentioned, is that you check basically all the 6 eigenvalues to see if they are positive here. And you can simplify the calculation because this log is a very tedious animal treat or whatever. So then you can sort of use the chain rule to simplify some of the calculations. So again, I will skip this part, it's not very important. But basically you can relate it to derivatives with respect to B. B is the left Cauchy-Green strain tensor. And you can use the chain rule to find the derivative of the left Cauchy-Green tensor with the logarithm of B. So this n is nothing but log of B itself. So you can use all of that to sort of simplify, and you can use some tensor to matrix mapping to convert it to matrices so that you can embed it into a finite element code and so on. Okay, so as I said, that part we can just skip. So the thing is like this. So when you start at the reference configuration, this Z is positive definite because actually one can show that the positive definiteness of this is equivalent to mu greater than 0 and 3 lambda plus 2 mu greater than 0. So when you start at the reference configuration, it is positive definite. Now you start the loading. Okay, at some point of the loading, if it loses positive definiteness, we say that it's a material instability. Otherwise, we say that the material is stable. So that's what is here. That it loses, if during the course of a deformation, it loses positive definiteness, it indicates that this stress has reduced with increasing strain, and hence indicates a material instability. So now let us see some specific examples now to see whether this criterion is successful in actually tracking these instabilities. Okay, what are the consequences of a material instability? So what will happen is suppose if you have a materially unstable model, then it can fail to converge. Your finite element code can fail to converge, or it can give absurd results. Because what will happen is that you will have two stresses, two strains corresponding to the same stress level. You can have that. So you can have all kinds of absurd results if there is a material instability. So the Savena-Kirchhoff model is known to have an instability. Okay, so let us examine this model under compression. So under tension, the Savena-Kirchhoff does not have any problems, but under compression, it is known that it has problems. So these are just the relations for the second Kirchhoff stress and the Cauchy stress in terms of the right Cauchy-Green and the left Cauchy-Green and so on. So basically consider this very simple example now where it is subjected to uniaxial tension. So if this T bar has a negative sign, it is compression. So actually I am going to consider the case where this T bar is compressive. I have shown it as tensile, but as I said, in tension there is no problem. Only in compression, the Kirchhoff model is known to have a problem here. So let us see this. So what happens is that if you keep on increasing now the compressive load, so what happens is shown here. So you can see that this is the compressive load. So as you keep on increasing the compressive load, the axial displacement keeps on increasing up to a certain point. Then what happens is that the traction suddenly reduces, and so the axial displacement keeps on increasing. That means the compressive displacement keeps on increasing, but this suddenly goes down. So this is one specific example. You can see that, and so this path is a non-physical solution path. So suppose if this material did not have this problem, this should have just kept on increasing. Basically that's what we mean by the notion of a hyperelastic material. But you can see that beyond this one here, it just dips. So you're keeping on increasing this, then the compressive load suddenly decreases. So that is what we call a non-physical solution path. Now, now what we want to see is whether this proposed criterion can detect whether an instability occurs at this particular point here. So here I have just stated these values for a maximum value of about this one. So that is this maximum value here. There are two solutions, right? While above this maximum there are none, because suppose if I apply something here, your code will not even converge, because there is no path here that goes beyond this particular fraction, beyond this compressive fraction. So this is the defect that I am talking about. Actually, it should continuously keep going up. So for any value of fraction, it should not fail this material model, but this will happen. So this is what we call as an anomalous behavior of the Kirchhoff under this tension here. So now let us see whether it tracks, whether the proposed criterion is able to catch that there is this material instability here. Okay, so as I said, you basically track the eigenvalues of this proposed tensor, which is this SZS. You can see that it becomes singular at this 0.606 here. So that is exactly here. So what happens is that, so actually this is the reference configuration. I have drawn it in the reverse way. This is the reference configuration and this is the stretch. So as I go along this direction, I am compressing the material. So I am starting here, okay, and here everything is fine. All the eigenvalues are positive. Then as I keep on compressing the material, right, when you come to this instability here, right, then there should be a problem. So here it shows that the eigenvalue has gone to 0. So you can see that. So these are the eigenvalues. It has not come out properly. This is the minimum eigenvalue. Actually, it has not come out. So the minimum eigenvalue just drops and it becomes exactly 0 at that exact point. So you can do this analytically, and you can then also track the eigenvalue. So it exactly matches it. So that's what is written here. So the path beyond that. So once it becomes 0, then you know now that there is a material instability. So here, this simple problem is considered because we want to validate, right? Just like you validate a finite element code, in the same way you want to validate whether this criterion works. So that is the reason we are using a simple example where we can test it first by hand calculations, whether the stress is increasing with strain, and then whether the criterion works. So that is the idea behind having a simple example, because you want to validate, this criterion. And so here also you can see that the peak, Cauchy and Kirchhoff. So I was mentioning about Hill's criterion. So that is based on the Kirchhoff stress. So you can see this slight shift here. So Hill's criterion will predict it at a slightly off value, offset, because that is based on this J tau. This J tau is J into tau actually, and this tau is the actual stress tensor. And so you will find slight differences between the predictions. So because it predicts it at a value where actually the material is stable, and the proposed one then says that it should be slightly off from here. And so we can see that the Savena-Kirchhoff model is flawed because because it doesn't satisfy this particular criterion. Then there is the Hinke model, which is a very famous model. Actually, this was proposed by Anand, and this gives, for rubber type materials, it gives very good predictions for reasonably large strings. Okay, and so here, so let's see what Hill's criterion says. So Hill's criterion actually predicts that this model is stable because you have, so these are the eigenvalues according to Hill's criterion for this Hill's tensor. And because we are assuming that mu is greater than 0 and 3 lambda plus 2 mu is greater than 0, according to Hill's criterion, this model is stable because irrespective of the scaling values. But actually, if you see, so then the proposed criterion, actually there is this additional factor here, and so most of the eigenvalues are the same, but here you have 3 lambda plus 2 mu, and this additional part is coming, okay, and that sort of messes up the whole thing here. And so the conditions now are that mu greater than 0, and also this should be greater than 0. So actually this, if you work this out, it leads to the restriction that the determinant of the deformation gradient should be less than E. E is that same, E 2 point whatever. So as a check, so let us now check whether this criterion is predicting it correctly. So you take F to be a uni-triaxial extension of this particular form, and then from the constitutive relation you can get this, and now so you can see this term is positive. Okay, then we just have to examine this term. So this term, it increases with j, as a function of j it increases. Again it peaks at E, okay, and then it decreases, just very analogous to the Savena-Kirchhoff model. So, so that means, again, we have a material instability at j equal to E. So according to Hill's criterion, we saw that actually this model is stable, but this is an actual physical example which shows that there is an instability at P, but that is not tracked by Hill's criterion because he is using the Kirchhoff stress tensor, whereas the actual stress tensor is the Cauchy stress tensor, and so this manages to get that because it says here that you have this criterion leads to that particular restriction, and so again in this case also it is able to predict that there is an instability in that model. Then this is the Blatsko model which I was talking about. This is known to be polyconvex. So now we want to show that polyconvexity is also not enough to predict a material instability. So here this model can be proved to be polyconvex. So this is based on John Ball's criterion. And but again, if you have a equitriaxial extension of this particular form, then again you can find the eigenvalues of this. Again you can show that it loses positive definiteness at some stretch value. And then again consistent with this, you can show that so basically we first find it by hand calculation whether the Cauchy stress is increasing and then decreasing, and we are also finding the eigenvalues of that and seeing if the two criteria give the same answer. And so here again you can see that it has a maximum at this stretch value. Beyond that it decreases. So beyond a value of this gamma of 6 raised to 1 by 5, it reduces. So both these criteria, the hand calculation and the eigenvalue criterion, they both give that there is an instability here. So even the polyconvexity is also not a sufficient condition. So our hypothesis is that this proposed condition is probably stronger than polyconvexity. And then there is one other Kravitz M condition, and one can show that also. So there are lots of. So that was regarding the material instability part. Now just a little bit on elastic instabilities. So here basically these are examples where you get non-uniqueness of solutions, right? The bifurcations, that if you have a slender rod beyond a certain critical load, it will go into this buckled shape. Or if it is a thick bar, then instead of buckling, it will go into a barrel shape. So this is known as barreling. And you also have this we are calling as a symmetric bifurcation, in the sense that if you have a square sheet of rubber, let us say, and this is This is even verified experimentally. So this is very interesting. If you have a square sheet of rubber and if you apply equal loads on the two edges, at a certain critical load, it suddenly goes into a rectangular shape. Up to that critical load, it stays square, but beyond that critical load, it suddenly goes into a rectangular shape here. So, so you can analyze. So again, we want to give a general criterion for when this happens, right? So I want to find out now. So give a criterion for when this happens. What is the critical load at which this goes into this particular bifurcation? So I'm not dealing with this problem or this problem. I'm dealing only with this problem. And that is what we call as a symmetric bifurcation. Fine. So here, basically, if you write out the variational formulation in terms of the first Elastic stress, then this is how it looks. And this is the linearized form of the first Elastic stress. So based on that, you can sort of see that this tensor, if it loses positive definiteness, then you will get a non-uniqueness of solution. Okay, so the criterion that we propose is that this tensor should be positive definite, that the first elasticity tensor should be positive definite. This symmetric, in that symmetric bifurcation, actually refers to the symmetry of F and not to the symmetry of the structure. Because we are considering only homogeneous deformation there, F is symmetric, and so that is what we mean by that symmetric deformation here. So here, basically the criteria in the literature, they have studied this problem again very extensively, but they have done the stability analysis on a case-by-case basis. That means maybe they will study a Mooney-Rivlin or Ogden or whatever. Some model they will take and then take that particular constitutive model and study the stability analysis. But here we want to propose a general criterion. That means it should work for any material. And so we propose this criterion that this A is the first elasticity tensor. We propose that, so these are tensors because that F is symmetric and so on. So this SAS should lose positive definiteness, or equivalently one of the 6 eigenvalues should become negative during the course of a deformation. Now again, the way to check this is again to check it against the earlier predictions from the literature, whether it actually loses positive definiteness. So these are some of the examples that are taken from the literature where people have studied, as I said, specific models. So this is a Mooney-Rivlin model, and this is just the stored energy function for that. And so if you consider the equi-biaxial, so that means it's a cube and you are loading it in the plane. Out of plane there is no loading. So this is a compressible Mooney-Rivlin material, and these are just some material parameters and so on. So here we see that the lowest eigenvalue goes to 0 at about this here somewhere. Here the 0 is here. The 3 point whatever is done here, 3.16 or something here around here. So this is the 0 value. It goes to 0. So that indicates now that there is a bifurcation at that particular point from a square shape to a rectangular shape. So that is the loss in the symmetry of the structure. So this critical stretch value again agrees with what is there in the literature. So here they have used slightly different constitutive models, so that is why there is a slight difference. But otherwise it is almost the same. So this was, as I said, this was done earlier in the literature, but done on a case-by-case basis. That means they had studied specifically this particular constitutive relation only, and it was not a general criterion. So this matches, this criterion matches that. Again, now this is a minor variant of that same problem where now you have some compressive load as well. So there is an equi-biaxial load in the plane, but out of plane also there is a compressive load here. And in this case again it will lose the positive definiteness at around 3.258, which is shown here. So in the literature there are some statements that if you only when the stress field is positive by positive again probably they mean that all the principal stresses are positive or something, only then you can have this bifurcation. But here in this example we saw that this load was compressive and even then it was happening. But in plane is tensile, but the out of plane was compressive. So it is not strictly true that you should have only a tensile stress. But at least this criterion is predicting that at this particular the bifurcation. And then this is just another example where if you have a unit cube triaxial loading, then again you get this bifurcation at this particular value, T by mu. So T is the load in the equitriaxial load here, that load T. And so what happens is that with this criterion, these 5 eigenvalues of these S, A, S are repeated and are lower than the remaining eigenvalue. And these 5 repeated eigenvalues become 0 simultaneously. So that shows that basically you get this bifurcation here at this point. And so again, this was also there in the literature. Hill had actually obtained this solution in a different paper. And so this matches again this criterion matches. So anyway, I will summarize now. So these are the conclusions of the talk. That basically we are proposing that these 2 criteria for a material instability. So this tensor Z, which is the derivative of the Cauchy stress with respect to the logarithmic strain, that if it loses positive definiteness, then we call that as a material instability. And for symmetric bifurcation, this is a necessary condition, not a sufficient one, that your first elasticity tensor loses positive definiteness. And the practical way to check these criteria are that you should check the eigenvalues of a 6 by 6 matrix, because you can convert these tensors to matrices using some tensor to matrix mappings. So you can convert them, and you can even, as I said, you can even put them inside a finite element code and things like that. A symmetric bifurcation is physically realizable. As I said, that in experiments you will actually get this. While a material instability actually indicates a flaw in the model that you are using. And so here, basically we should modify. So for example, Savena-Kirchhoff model, you should not use beyond a certain compressive regime. Right? Beyond that certain compression ratio, you should not use the Savena-Kirchhoff, because after that you get this material instability. So you should use the Savena only in that limited dose, or you should use some other model which is more reliable in some sense. And so we have shown by means of various examples that these 2 criteria are successful in detecting these instabilities, whereas the other ones either fail to detect them or predict them at an incorrect deformation state. And you can use this to find bounds also on material constants of some newly proposed material models. So as I said, you have to actually test it on all possible loadings, but that is impossible. So basically you can test it on some critical states of loading like uniaxial, biaxial, and triaxial. I think that's it. Thanks.
In one of your slides, you have shown that after a particular stretch value, the compressive stress is going to decrease.
Yes.
And you have shown that the stretch value is 0.6 at that
Yes.
Is that particular stretch valid for any hyperelastic?
No. That is a particular problem with the Savena-Kirchhoff model. That's what I said. So let me just go back there. No, it doesn't happen with every. So I'm considering a specific model. So this is a flaw with the Savena-Kirchhoff. So other models may or may not have this flaw, but this is specifically the Savena-Kirchhoff has a problem under very high compressive loads. I mean, if you use it for moderately large compressive strains, it will be okay. But only when you take it to this value, this point whatever it was, 0.6, this one. Only then, after that point only it has a problem. Up to that point it is okay.
But if someone wants to do the experiment like on hyperelastic model, hyperelastic material, if someone wants to give the compressive load on that particular material, then what sorts of straining someone has to give to the material?
So, I mean, mostly for such large strain, maybe you can do it only with rubber, maybe, because for other materials it may go into some plasticity or something. So this is a very, as I said in the beginning, this is very idealistic in the sense it is assuming pure hyperelastic material and all that. So if you actually take it to those very high strains, it may either fail or it may go into plasticity and so on. But except for rubber, because rubber can withstand large strains. So maybe in the case of rubber you can test it. But for rubber anyway you don't use Savena-Kirchhoff. You will use maybe like Ogden or Munir-Rivlin, those kind of models. You will not use Savena obviously. Savena you may use for steel or some other type types of material, but not for rubber. For almost incompressible, you'll use either Munir-Ullin or Ogden or those kind of models.
And one more question.
Yeah, sure.
In one of your slides, you have shown the in-plane strain. In
Yes.
which plane you are calculating that in-plane strain?
No, that is that. This one, I think here the loads are being applied in plane.
No. Later on, one in-plane strain curve is there.
Later on.
Yeah, in-plane stretch.
Oh, okay. No, that in plane is the xy. The out of plane is the z. Let us say. So you are applying the load, the tensile load in the xy and the compressive load in the z. So the in plane refers to the xy. So those are equal, and they will remain equal until the critical load, when suddenly it will go into that other state, which is rectangle. It will go into a rectangle. In that plane, it will go into a rectangle. In the xy plane, it will become a rectangle.
And one more curve, you have shown the stretch value up to 4. I am wondering that how that stretch value will be up to 4. Previous curve, just
Yeah. No. These are all.
Up to 4 you have shown the stretch value up to 4 in the compressive load.
No. As I said, this is a theoretical study. I am not claiming that actual materials can withstand that kind of. I am just saying that.
But in actual case, what I understand that up to 0.95 or something like up to 0.05, because if initial thickness of the material is 1 mm,
right,
it can be compressed up to 0.05 max.
Yeah, but this is in the tensile one. This is not compressive. This is tensile. Here you are applying tensile load. You are not applying compressive load. This is positive. Greater than 1. This is not less than 1.
But negative stress value, it is negative.
No. These are all, okay. That is after. After that bifurcation that is happening. But so what we are showing is that this is not the stress. This is the eigenvalue. This is the lowest eigenvalue. It says here lowest. It has not come out properly. It says lowest eigenvalue. So the lowest eigenvalue becomes 0 here at around 3.16 here. Yeah, it's not a stress. It's an eigenvalue. Just to show that the criterion. Right. Those are the existing ones.
Yeah, so I fail to appreciate why this criteria is better than the other in this sense. That what appears to me that I will give a criterion if it fails this it is instability.
The proposed one.
For all criteria. This is a criterion, if it fails the criterion it is called unstable.
Right.
But that is not how one would like to think of instability. It should be a more physical.
No, but that is what I said. That is the in verbal terms. It is that stress should increase with strain. That is my verbal statement. I am trying to make it into a mathematical statement. And what we are showing is that all these criteria. If you take the Savana-Kirchhoff material example, there the stress increases in magnitude for the compressive thing, and then it reduces. So all those criteria they fail. I can show that. All those details I did not show. But the Baker-Erickson fails, the tension extension fails, polyconvexity fails to predict that at that strain value, the stress decreases with increasing strain.
So you are saying instability is when the stress versus strain curve goes through a peak.
Yes, but that should be the true stress and the true strain. It should not be the.
So again, so if I say that let's define stability. The instability is when true stress, true strain graph goes through a peak.
Right.
And for that.
For a hyperelastic material, for very idealistic, I am not talking of real life behavior. Yeah.
I think that is instability, and this is a criteria which will capture instability of this definition.
Yes. Yeah. No, but this statement about stress increasing with strain is there in the literature. That I am not making up myself.
No, in the sense that instability, see, my little experience I have is that there are, for example, there is Lyapunov definition of instability.
Right.
And then there is later on this got converted and it became
think that's the same, almost the same.
It might be, I am not very good.
Yeah.
But I do know that diapno may imply Hadamard, but Hadamard will not apply here.
Yeah.
But through the ages, people lost this touch. So nowadays, people end up putting only Hadamard, while they are still seeing diapno.
Okay.
Okay, so I am trying to put this in that context that.
No, so what I'm trying to say is that verbal statement has been there forever. I'm not changing the verbal statement. The only thing I am changing is the mathematical statement corresponding to that verbal statement. That's all that I am changing. So all those inequalities are actually trying to capture that concept of stress increasing with strain. But as I said, if it had been 1D, it is trivial. The whole complication arises because of the 3D nature of the problem.
If I understand correctly, this If I understand correctly, the conditions are like this. They say if x is less than y or whatever, then it is unstable. Or they say if x is less than y, then it is stable. I mean, you understand? Are they statements of when instability occurs? Or are they statements of when you can still conclude that it is still stable? Are they inequalities from
No,
the
they are trying
side,
to.
or are they
No. See, all the inequalities are trying to figure out whether that particular model, the constitutive model, is giving reasonable predictions or not. That is what they are trying to figure out. So they are actually the inequalities are all in terms of either stresses and stretches, or stresses and strains and so on. But you are applying each of those inequalities to particular model. So I will apply to Savena, I will apply to this, I will apply to that, and try to figure out whether that particular criterion captures that. Suppose if there is an instability, whether it captures that instability when I apply that particular inequality to that particular constitutive model.
Let us say that the condition is if so and so inequality is satisfied,
Okay.
then it is stable.
For all possible deformations.
I understand.
Yeah.
It is stable.
Yes.
Conversely, if the inequality is violated, then it is unstable.
Correct.
Okay.
Yes.
Now, let us say instability is easier to detect.
Right. Correct.
So, are there situations where it predicts instability, but instability is not there? Have you found such examples? You understand?
Means some criterion. Some criterion related.
Yes. I think there was one.
Yeah, there was that Savena, I think.
Because if I understand, there are situations where you have found instability,
Right.
where these inequalities have not yet predicted that instability.
Maybe here. So Hill's criterion is predicting it at a wrong stretch value. So here it is predicting it at some 0.7 or something like that. Whereas the actual thing is happening here. So actually the material is stable at 0.707, but it says that it is unstable. I don't know whether that answers your question. So at 0.707, the material is actually stable, but the criterion, Hill's criterion, is saying it is unstable.
So it predicts instability too early.
Yes, too early. Yes.
Because you are coming
Yes,
from one.
yeah, you are coming from there. You are coming from one actually. That's right. You are coming from.
That is it. You all get it right.
Yes, because it predicts it at 0.606. That is where the eigenvalue. Let me just show that. Yeah, the eigenvalue becomes 0 at 0.606.
No, but you are comparing your criterion with Hill, or you are comparing both of you with something else?
No. So one is that I can do a hand calculation by just varying the stretch value and plotting tau. That is just a hand calculation. I am comparing against the hand calculation because that is the true thing, right? That is the correct. That is like an analytical solution. That is like an analytical 1D solution. And I am comparing it. So both criteria I am comparing against the analytical solution, right? Because that is the true solution. So yeah.
If I understand it correctly,
Yeah.
say you have a stress versus strain behavior,
Right.
and you have a definition of instability there,
Right.
and you want to translate this definition of instability to the elasticity tensor or the material constant.
Right.
Now, the proposed criteria so far are not matching the stress value at which the actual instability.
Or they are predicting that something is unstable, something is stable. So those also, not just the value, sometimes even that prediction is wrong. Like for the, just to give an example, this one. Here, so it says that actually it is stable. Hill's criterion is saying it is stable, but it is not, because on the next slide I have shown that it peaks at, so this is now an analytical solution. This one is an analytical solution, and it peaks, so this you can easily do by hand, and you can show that it peaks at E and then decreases. So that is what I am saying, that I am comparing it against analytical solution, I am not comparing it against just another criteria.
Analytic meaning numerically computed stress versus strain curve.
No, this you can do by hand.
Specific loading condition.
Yeah, for a specific, for a specific loading. Yeah, exactly, for a specific loading.
So these are examples.
These are examples, yes, these are examples.
And your criteria based on this tensor Z matches.
Yeah, so that's what it is. Yeah, because it's so that is so according to this criterion, exactly less than E. That's what it predicts. Det F less than. So that is J is det F. So it predicts exactly.
Do you know any example where your criterion doesn't work?
No, you find it.
Okay.
Yeah.
So it seems to me that there are instabilities that are predicted or not. Unfortunately, none have been seen because they're all in the plastic region.
Yeah,
There's no material which could ever use any of these criteria.
no, except for rubber. I mean, like
But rubber has a very particular constitutive equation,
right.
and then it will be stable for any test.
Yeah, so as I pointed out in the beginning, this is a theoretical criterion in a
But
perfect
the-
world. In a
Yes.
perfect world.
But automatically you're isolated from the real world.
Yeah, that is true. No, that is
Anything you say is
Yes.
not applicable to the real world.
no, but as I said,
Okay.
for rubber it may be. For rubber, for large, it can undergo large stretches, so that those.
But then you can't consider a range
No,
of
not
specific
for
equations.
this. I'm saying for this one. For the elastic instabilities, these predictions can be seen in experiments.
Sure.
So that it can
Just
predict.
wanna squash it.
That it can predict. So.
Can we know what are the number of problems that we need to solve to change this criteria?
No, yeah, that's a good question, because as I said, actually one has to test it for all possible developments, and that is just not possible. So that is why what we think is that uniaxial, biaxial, and triaxial loadings may be the critical, because that is where we have found most of the instabilities. We think that may be the most critical loading condition. If you test it for these conditions, maybe, and if a model passes these tests, maybe it passes others. But that is just a conjecture. I mean, I have no proof for that.
Like for instance, for torsion problems, etc.
No, torsion, okay, that means like if you have shear stress. Yeah, that's a good question, as I said, but we didn't try it for, I mean, loading in this, tension loading in this will correspond to shear in some other plane. You can think about it like that.
If you have the problem compressing one and
Yeah, correct. So that is what,
automatically
yeah. So in some other plane it is like a shear. So maybe that in that sense. Yeah.
Few things.
Yeah.
So first of all, as I understand, all the available criteria, there are sufficient conditions for stability. Let me complete. Yeah.
Sure.
I'm not seeing a necessary condition for stability. So what makes you think that this criteria is also a necessary condition?
No, necessarily we are just defining that material. We are just defining. Actually, it's a definition. So that's why when you define
should
it.
have some basis of.
See, I mean, basically, see here. Let me just go to that here. So here, see for the symmetric bifurcation, the reason I am saying that this is only necessary and not sufficient is I can prevent by putting some constraint. Like in a buckling problem, I put pins here. Then it will not go away.
Let us not get into.
No, that's what I'm saying. But here, this is how I'm defining. I mean, I'm just defining it that stress has decreased with strain. Then I'm defining that as a material instability. So I'm calling it as a necessary and sufficient condition. By definition.
Conjecture.
I mean, it is a mathematical statement corresponding to my verbal statement. That verbal statement
is a conjecture.
No. What I'm going to say is this is how I'm defining that the material instability, and so okay. What you're saying is why is it if and only if?
See, I think just if I may take some more time.
Yeah.
Connecting to what Ishan was also mentioning.
Yeah.
What is, the the way I have usually seen these things being done, starting from Leibniz's idea of stability, we start to get more and more sufficient conditions. I mean, we come to convexity, we find convexity too restrictive. Then you see quasi-convexity, right? Which is a sufficient condition for stability. Now, quasi-convexity is also sometimes very difficult to check. That's why you have polyconvexity, which is a sufficient condition for convexity, but not necessarily condition.
Correct.
So, and polyconvexity, as it turns out, is easier to check. So here I see a very definite link. That I have a very clear idea of stability as stated by Leibniz, very widely accepted. Which I do not want to violate, and which I understand as stability. Now, starting from that, I have this series of sufficient conditions. Rank bound convexity is again a sufficient condition for quasi-convexity. So there I see the whole link of arguments. And all these conditions are on strain energy density. So they're not talking explicitly about stress and strain. So this is a slightly different class of, but most of these are, I mean, as I understand, most of these are obsolete. Baker-Erickson, no one uses Baker-Erickson anymore. No one uses Coleman.
No, but that's the reason I.
Maybe. But even in non-linear elastic relation, no one is using these things anymore.
Just one second. So this is a polyconvex model.
This one would. So what you are saying that this is something that I am not able to digest, because what, according to established results, I mean established proofs, polyconvex, I mean if a material is polyconvex, then it...
No, it is just a mathematical condition used to prove existence. But there is no link with
No,
physical
I'm not
reality.
talking about existence, I'm talking about stability here. See, polyconvexity has been used for, as I said, it is a sufficient condition for quasi-convexity. So violation of...
Yeah, but see...
So violation of polyconvexity actually means instability. Now, of course, satisfaction of polyconvexity does not, since it is not a condition. Satisfaction of it is nowhere being said. What you are talking about existence is a different problem altogether. Polyconvexity is also seen.
But what I am trying to say is that polyconvexity still cannot say that, okay, there will be an instability at this stretch value. That it cannot say. Here we are proposing a criteria that says that at this stretch value, the positive definiteness is lost, and this is where the material becomes.
You are right. You are absolutely correct. But I do not see a basis of this criteria. See, as I said, I am talking about the whole sequence, I start with the Leibniz notion of stability, from where I can systematically prove a sequence of sufficient conditions. But here, so that's why I am asking you whether this is a conjecture, both sufficient and necessary.
This is a conjecture, and that may be a conjecture. I mean the if and only if.
Both the things. I mean that your criteria is conjecture, which you have tested on few examples. But it might be wrong or it might be right.
Yeah, it is a conjecture, that is true. It basically, see, there are so many existing inequalities, like Baker-Erickson, tension extension. This is one more. This is one more. So,
I think that is if I understand that,
strong electricity is not a conjecture. Strong electricity is a sufficient condition for stability.
no, but
I understand what you mean by Lyapunov stability. Lyapunov stability refers to dynamical system. There is a trajectory that goes from time 0 to all time. There is no trajectory over there.
it is just a sufficient
displacement. You can have it in terms of displacement.
No, Lyapunov stability is defined. There is a t. You can call it x, but x has to go from x0 to infinity. Over here, there is just some strange state. Actually, something happened.
In terms of
Displacement.
I mean, here, strong electricity does not meet this physical requirement.
No, but there is no trajectory. There is no time.
No, but see, this is so exactly too strong. This is too strong. This is too strong. So that is why.
Or too weak, I would say. Too weak. Not too strong, actually, too weak.
Quasi-convexity will also not satisfy.
So, what we are trying to say is
Which
that
means that these restrictions do allow for non-linearness. Actually, that is why these restrictions are.
Coleman mode doesn't allow.
Coleman norm is not there in this picture at all. As I understand, the Coleman norm is
I knew that this would be a controversial topic. I knew that. So,
I think we can take questions also.
today's dinner will be orthodox.
So let's thank the speaker once again.